Greetings. We are going to design a couple of simple circuits. These are very important circuits in constructing a computer. So one of them is what's called a decoder. And here's the way a decoder works. I want you to imagine that there is a box here. And let us suppose there are 4 wires coming out of them. And if you like, you could even imagine that these wires are connected to an LED, some kind of light or something like that. And what I would like to be able to do is there's going to be some input. We haven't quite determined what that is yet, but here's what I want to do. I want the option of either this outputting a 1, and these would be 0, or, depending on the output, I would like this to put out a 1 and everything else is 0, or it might be the case that this outputs a 1 and everything else is 0. Or something like that. These are all off and that's on. So first of all, notice over here, there are 4 options. And in fact, I think what I'll do is I'm going to give each one of these lines here a name. And I'm going to call this, that's a script O, and I'm going to call that O0. And I'm going to call this O1. And I'm going to call that O2. And I'm going to call this O3. So now I have to think, remember, these are the outputs I want. So now I have to think about, well, what kind of input can I have that I can pick one of these 4 outcomes here? And it seems to me that my input would need to consist of 2 bits. Remember, if I have 2 bits, and I'm going to call these S0 and S1, if I put a 0, 0 there, I want this outcome to occur. So this would be, I'm going to say input. So for this one it would be 0, 0. And for this one over here, the input should be 0, 1. And for this one over here, it should be 1, 0. And for this one over here, it should be 1, 1. In other words, you could think of this as a 2-bit unsigned binary integer that's basically selecting which output line is going to go high. Well, designing this circuit is actually pretty simple. And what's going to happen here is I'm going to have an AND gate here. And I'm going to call this one over here O0. And I'm going to have an AND gate here. And I'm going to call this output O1. And there's going to be an AND gate here, and that will be O2. O3. And over here, I am going to have S1. And over here, I'm going to have S0. Now, what I'm going to do over here on the input to these, I'm going to invert both of the inputs. And I'm going to have S1 go into there, and I'm going to have S0 go into there. Okay, now these are both input. So you can see already when S0 and S1 are both zeros, what happens is they both get inverted. So now there are 1s going into this AND gate, and there's going to be a 1 coming out of here. And what I'm going to do, I'm going to fill in the rest of these here. And here, I'm going to put it on the bottom. And here's what this is going to look like. So I'm going to come down here. And I'll draw the whole circuit for you first, and then we'll go ahead and we'll discuss it. Okay, so now, again, let's go back to the example of 0, 0. When I put a 0 on S0 and a 0 on S1, and the reason why I use S is S stands for select. Okay, if I put zeros on both of these lines, you can see they both get inverted, and what's going to happen in here is there are two 1s going into the AND gate, and I get a 1 out here. On the other hand, think about it, if these are both zeros, here's a 0 going into this AND gate, there's a 0 coming out of here. There's a 0 going into this AND gate, there's a 0 coming out of here. There are two zeros going into this AND gate, so there's a 0 coming out of here. Okay? Let's consider another example. Suppose I were to have S1, S0. Suppose I were to have a 1, 0. Okay? Well, if I have a 1, 0, here's a 0 going in here. That's going to put a 0 on there. If I put a 1 and a 0 on here, you can see what's going to happen is this is going to get a 1, and that 0 will be inverted to a 1, and O2 would output a 1. Notice this is a binary 2. If I were to put a 1, 0 onto here, notice there's a 0 going into an AND gate. So what's going to happen over here is there's going to be a 0 coming out. And notice if I put a 1, 0 here, the 0 becomes a 1, but the 1 becomes a 0. 0 input to an AND gate outputs a 0. So this is what's called a decoder. And you can see that basically decoders have a structure that kind of looks like this. The input is N select lines. And what's coming out is 2 to the end output. Okay, so you will see people refer to decoders as a 1x2 decoder, or a 2x4 decoder, or a 3x8 decoder, 4x16 decoder. And that is the story of decoders. Okay, our second circuit is sometimes what's called a MUX. MUX is just another name for a multiplexer. Okay, and the way that a multiplexer works, here's how you see people draw the diagrams for multiplexers. I'll give you an example. So I might call this I0, I1, I2, I3, and down here is the output. And what happens is one of these lines has to be selected to be the output. Well, if I've got 4 lines over here, what's going to happen is over here there would be 2 select lines. So there would be select 1 and select 0. So the whole idea here is the following, that, for example, if I0 had a 1 on it, and I would have put a 0, 0 here, then I would see a 1 coming out of here. In other words, whatever on this line would go through here. If I were to put a 1, 1 over here, what that would be doing is that would be selecting this line 3 right over here, and that would be what would come over here. Okay, so when people talk about multiplexers, you'll either see them, they'll say things like this. They'll say there's a 2x1 multiplexer, or a 4x1 multiplexer, or an 8x1 multiplexer. Okay, this number over here is referring to the input lines. And of course, what's not being specified here is the select lines. But this would have, a 2x1 would have one select line. This would have two select lines. This would have three select lines. Okay? So let's talk about how we make one of these things. And it's going to look kind of familiar to the decoder that we did before. So what we're going to construct here is I'm going to make a 4x1 multiplexer. And what I'm going to assume here is here is I0, and here is I1, and here is I2, and here is I3. And what's going to happen is down here, I'm going to have an AND gate, and I'm going to have an AND gate, and an AND gate, and an AND gate, like that. And I'm going to have I3 go right into there, and I2 go right into there, and I1 goes right into there, and I0 goes right into there. And the other thing I'm going to do is I'm going to have all four of these lines go into an OR gate. And down here is the output. And now I have to take care of these select lines. So over here I'm going to have select 1. Over here I'm going to have select 0. And this should look familiar to you. Over here I'm going to have two inverters. Over here, I'm going to have an inverter over there. Over here, I'm going to have an inverter over there. And you can see that what's going to happen, I'm going to draw S1 across. And I'm going to do this. And then I'm going to draw S0 across. Important to draw these. Okay, now let's go ahead and analyze this. So suppose S1, S0, suppose I have a 1, 0 on there, and suppose this has a 0, 1, 1, 0. Now, this circuit over here, part of it, at least with the select lines, this is going to look very similar to a decoder. So if there's a 1 and a 0 on here, first of all, we can see that what's going to happen here, if there's a 1 here and a 0 here, there's a 0 going into this AND gate here, and there's a 0 coming out there. If there's a 1 and a 0 going in here, okay, I've got a 1 going in here, the 0 will get inverted, so there's a 1 and a 1 going in here, and what's going to happen is so I have two 1s over here, and if I2 was 0, a 0 would come out, and if I2 was a 1 would come out. What I'm going to say is what comes out of that gate there is just whatever I2 is. Now in this situation over here, if S0 is a 0, there's a 0 going into this AND gate, and there's a 0 coming out. And you can see over here, if S1 is a 1, then that 1's going to become a 0 here, and what's coming out of here then would be a 0 as well. So now, if I'm ORing I2 with all of these zeros, what comes out of here is an I2. And you can see that's what we specified on our select bits here, and so that's what passed through right here. You can try this for other combinations of these bits, and you'll see that what gets passed through, there'll be zeros on 3 of the AND gates, and on the 4th AND gate, it'll be whichever one of these was selected by that. Okay? Multiplexers. Pretty cool. Here's a homework assignment for you. I gave this in class. I'll give it to you now. I want to suppose that you have a box of 2x1 muxes, and you also have wire, and the problem is make a 4x1 mux. It's a homework problem for you to think about. Okay, on to the next one. Greetings. Our third circuit, we're just moving along here. We're going to talk about something called a half adder and something called a full adder. Okay, and as you guessed it, these add bits. They do addition. And the idea here is the following. We'll first talk about the half adder. Half adder, full adder. So here's the half adder. So you can think of the half adder as being this box. And there are 2 inputs here. There is, I'm going to call it input 0 and input 1. And what comes out of here is the sum. And then there may be a carry. Okay, so in other words, we know if I'm adding bits, well, 0 plus 0 is 0, 0 plus 1 is a 1, 1 plus 0 is a 1, and if I go 1 plus 1, we know that that's going to be a 0, and then I've got to carry a 1 over to the left. Well, that would be what this carry is right here. So the truth table for this is pretty simple. I1 and I0. And actually, if you think about this, there are 2 different functions that I'm defining here. One is called sum, and one is called carry. And I have 0, 0, 0, 1, 1, 0, 1, 1. And in this case, I've got 0, 1, 1, 0. And in this over here, there is no carry, there is no carry, there is no carry, and over here there is a carry. And the creation of this is pretty simple. We can see that it's right over here. These 2 are the ones that give us a 1. So what I need to do over here is I'm going to have I0, or I1 and I0. And this over here corresponds to an AND gate that looks like this gets inverted and this one doesn't. And this one corresponds to that one doesn't get inverted, but this one does. And this is the sum. Okay, does everybody see this over here? If I1 has a 0, this inputs a 1 to it, and if I0 is a 1, there's a 1 in here, so I'd get a 1 and a 1, there's a 1 going in there. And that's what would come out. Remember, if this is a 0, 1, it's going to be a 0, 1, there'd be a 0 coming out of here. So I'd have a 1 from here and a 0 here, but it would output a 1. Likewise, if I were to make this a 1 and make this a 0, well, there's a 0 going in there, there's a 0 coming out. But if this is a 1, there's a 1 going in there, and if this is a 0, the 0 becomes a 1, gets inverted, so that's a 1 and a 1, and I would output a 1. So these 2 terms here give me the sum, then the carry, we can see I have to have something that looks like this. Okay, this is very simple. Carry. So here's a half adder. Okay? Now, there is something called a full adder, because here's the issue. Suppose I want to add suppose I wanted to add these. Okay? Now we can see over here 1 plus 1 is a 0, and that's carry the 1. And then I have a 0 plus a 1 plus a 1. Well, that's a 0, carry the 1. And then I go 1 plus 0 plus 1. Well, that's a 0, carry the 1. And then I have 0 on 1. Well, that's a 0, carry the 1. Oh, look at that. Isn't that interesting? Now, I'll leave it to you. Is there an overflow? But here's the point. This bit right over here, adding those two bits, that can be done with a half adder. In other words, there are two bits coming in, and what comes out is a sum and a carry. But now, when you get to these over here, the input is not only two bits, but the carry from the preceding one. So for a full adder, what you have is it's going to look like this. There's something that gets coming in, and I'm going to call that the carry in. And then there is also A and B, and what comes out of this is a sum and a carry out. Now the carry out, of course, comes over and it goes over to the next full adder over here, where there is also an A and a B. I know it's getting messy here. And what comes out of here is a sum and then another carry out. So what's happening here is you actually have, when you want to add, suppose I wanted to add two 4-bit numbers, this over here is a half adder, this is a full adder, this is a full adder, this is a full adder, and what's going to happen is we have this carry comes out of the half adder into a full adder, and then what happens is these have to be wired like this. And then down here, these are the sums. Like that. And there's a name for this. This is called a ripple adder. The reason why it's called a ripple adder is because for this to get the correct answer, it has to wait for this one to finish, because we have to wait for that carry bit to come over here. And for this one to get the correct answer, we have to wait for this carry bit to come over here. So this one really has to wait for this one and this one. Finally, this one over here, to get the correct carry in, has to wait for these three. So you can see that the longer this chain is, the slower the whole process is. Okay? So the question is, what does the truth table for a full adder look like? Well, there is A and B, and there's something, I'll call it C in, there is the sum and then there is C out. Okay, so the sum here is 0 and there's no carry. 1, 0, 1, 0. Over here there is a 0 and there is a carry of the 1. Over here there's going to be a 1, 0. Here there's a 0 and a 1. Over here there's a 0 and a 1. And over here there is a 1 and a 1. So now one would have to go ahead and remember, these are two separate circuits here, the sum and the C out. And I can see over here that the sum, I see 1, 2, 3, 4. They're going to be 4 AND gates here. There's an AND gate. There's an AND gate. There's an AND gate. There's an AND gate. And we can imagine that from top to bottom it's A, B, and C in. So over here, I've got A, B. Over here, just the B signal is inverted. Okay, over in this one, it looks like B and C are inverted. And in the last one, it looks like none of them are inverted. So I'm going to have A, B, and C in. So here's A. So that goes right in there. Right in there. Right in there. Right in there. Here's the B line. Goes right in. Here it gets inverted. Here it gets inverted. Here it gets inverted. Here's the C in line. Goes right in. Here it gets inverted. Straight in. Straight in. And now these all get fed to an OR gate. And we do that, out, sum. Okay? And I leave it as an exercise for you to go ahead and construct a similar circuit for C out.